João.
Yeah, so there was discussing some logic just before I started the topic of this lecture, maybe the right of the Polish, the projection of my name onto the Polish language could be something like this. If you pronounce, for those who speak Polish, you pronounce something like this, it's a good approximation to my name. Yeah, it's João. Ramos.
Ramos, but the first.
João.
João. Like it's written, yes.
Yeah.
Yeah, that's very good actually. Yes.
Somebody.
Just read Literally, it's a very good approximation. Yeah, so yeah. With that out of the way, thank you so much for inviting me. Yeah, so we're gonna, as Quadri said, we're gonna be talking about time frequency representation and other topics. And so the plan for this lecture series is to take it very slow through the world of time frequency representations and, well, what some people would call time frequency analysis, but surely my PhD advisor would he would be disgusted to hear me calling that time frequency analysis for sure, because it has a completely different vibe to what he's used to studying. But anyway, so let's, without further ado, let's maybe start with a bit of motivation towards what we want to do here. So we start with the Fourier transform for an L1 function. And yeah, I'm sorry about this normalization. There's already a typo. So yeah, it's went by really fast. So already typed on the first slide. It should be mine with everything here. But yeah, so take a Fourier transform with the usual normalization of -2 pi I. And well, the fundamental question that probably all of us in this room have come across is how to recover f from a reasonable amount of information from f and f hat. Right? So we have to make sense of what is a reasonable amount of information. But yeah, so we don't want to have to pay the price of asking too much information on f and f hat, but we want to have, on the other hand, a satisfactory reconstruction recently. Applications of such a problem are present, as many of you should probably know, as in many areas of mathematics, but also like in physics and engineering. So some of the most famous examples are in signal processing, crystallography, radar and sonar sensing as well, with the phase retrieval problem, and several others of a related kind. Okay, so let's maybe talk about a couple of attempts to recover f and f hat from a reasonable amount of information, right? So the first one is where, well, you take as much information as you can get. So you take all of f hat. Then of course you can recover f by Fourier inversion. But it's for sure too much information. So we're like, well, can we do better than that? And next example says, well, in some cases you can. Well, and that's what the Shannon-Whittaker interpolation formula says. So let's break this formula down. So it says basically, well, suppose that f hat is supported in an interval -1/2 and 1/2, and it's an L2, right? Then the Shannon-Whittaker formula says that I can reconstruct f explicitly from the values of f at the nodes n, where n is an integer. Right, so for this formula with the same function, beautiful stuff. But of course, if for people in signal processing, they would stop right here and you would be very happy because, well, all signals are kind of band limited for them. So all good. But if you're looking into the mathematical side, the pure mathematical side of signal processing, you might note that, you might remark that the issue, that there's an evident issue, right? So they're not all functions that we consider in our lives are going to be compactly supported on the Fourier side. So how can we overcome this barrier? And there's I always like to highlight this result. It's one of the most beautiful results I know in recent and modern Fourier analysis, which is the Radchenko-Gazovsky Fourier interpolation formula. So what does it say? So it says that, so the Racine and Biazowski were able to construct a sequence of Schwartz functions, an, such that if I give you an f, which is even and sufficiently smooth, then I can recover it and decase like at a sufficiently high level, right? So it's like a 1 plus x to the minus a certain high power. Then I can reconstruct f from its values at roots of integers and the values of its Fourier transform at roots of integers, positive integers, right? So the function is even. Explicitly in the functions an, where the functions an are the ones that constructed. It's a beautiful result. It's a super powerful result. It's related. It's directly related to the sphere packing problem. Actually, Marina Biazowski comes from the idea that Marina Biazowski used in order to solve the sphere packing problem in dimensions 8 and 24. She actually, well, as a consequence, as a byproduct of her techniques, one is able to construct an interpolation formula like that in dimensions 8 and 24, but with derivatives. And this formula actually solves the sphere packing problem through linear programming bounds. It's a very interesting theory, but let's maybe not focus too much on it here. And but well, as beautiful as this formula might be, there's also like an evident issue, which is that, well, the interpolation basis an, it is complicated. So the reason why I'm not explicitly writing that is that there is no reasonable explicit formula for that. They have like a formula in terms of Laplace transforms of certain quasi-modular forms or something like that, which is you can work with in order to prove bounds, but you cannot work with, for instance, in order to find all the zeros of an. It's still like a very important open problem in this field to try to find the like all the zeros of these functions an. It has implications to many stuff, but in any case, it's a complicated function. And the formula above is not so practical if you really want to have extremely good numerics for a function f, at least at a first second. It's still like a very incipient kind of a theory, so we could, if one works a little bit more in depth, it might be possible to develop it to the point where we have sufficiently nice estimates on an, so that we can be worked with. But at the moment, it's still very far from any practical application. Okay, so the bottom line is these methods that we saw, as much as they actually give us a sufficiently good mathematical way of recovering a function from space and frequency values, they might not be enough in order to recover f if you want to obtain more intrinsic global information about f. And one has to develop a theory adapted to that. So what do I mean by that? Well, let's maybe quote Heinz Kirchner, who's I think it's the best description possible is what I'm going to be telling you guys. So Kirchner in his book Foundations of Time Frequency Analysis basically says the following. So let us think of f as describing a piece of music, right? As a physical quantity, f of x may be, so could be describing the amplitude of the vibration of a speaker membrane or an electrical current at time x, right? So let's think of it that way. Does f describe the temporal behavior of the signal? So you can you're able to infer temporal behavioral patterns of that, and therefore some rhythmical patterns of the piece of music that we're observing, we're listening. However, we would be hard pressed to determine the melody of f of the music or its key by looking at f alone. So that, on the other hand, by looking at the dominating frequency bands of f hat, one might be able to recognize the key, but neither the rhythm nor the melody will be apparent. So if you take a look at what this is saying, basically rhythm can be obtained by observing space behavior of the signal, and the key by observing like frequency behavior, but like the melody, which is that fine property of this piece of music you're listening that your ear can actually discern, neither one or the other alone can do it. So we need something that combines. And as it says, although both F and F hat contain all possible information, neither of them shows the relevant information that can be heard by the ear. At any given moment, the ear perceives the bare signal F and processes F into a representation that provides simultaneous information about time and frequency that we call music, and that we call the melody of music, and that we understand as a melody. Okay, so what we actually want is to make sense of this thing in mathematical terms. So what the heck is actually this kind of operator that is being described here, right? So in musical terms, the musical score does that very well. So at any given moment, you know exactly what the rhythmical patterns are, but you know actually also what the frequencies are, but just looking at how high or how low everything is. So the musical score is actually a time frequency representation if you start to think about it. But then, it is a very, let's say, a very discretized one, because as we know, the notes are not played at like direct delta intervals. There is, of course, resonances, and we can actually, we can discern between them, but the musical score is a very good approximation to that. On the other hand, in a mathematical, more mathematical notion, we have to make sense of that, what that would be, right? So we don't want only a representation. We want to define an operator that accomplishes the analysis that we want. So the idea for such a representation is, well, let's first restrict your function such that we can analyze it once. Its space and frequency components. So in the following way. So first, take an interval in the real line and multiply the function that we're analyzing by the indicator of your input. Okay. Now look at the Fourier transform of this product. It's going to be just a convolution of f with the indicator with the Fourier transform of the indicator of the interval I. And now we actually take it and restrict it to an interval ij. Okay, so then we define Fij at a real value S to be the inverse for a transform of exactly this Fi hat times the indicator of J. In other words, by using Fourier inversion, this is the same as taking Fi convolving with the inverse Fourier transform of Ij, which should be something like this, right? So this should be more or less the formula that we have for Fij, which is the representation that we want in a way to be kind of well localized in space and frequency. So let's maybe, I don't know, let's maybe think of J and I, since we're kind of like thinking about it as like shifting the frame at which we're observing our function. Let's think of J and I as a translation of, as translations of two fixed intervals, right? So J will be a translation T psi of J naught, and I will be a translation Tx of I naught. Okay. Yeah, and then we just insert basically what this means into this definition of what do we get? Okay, so we get Fij is just an integral on R of f of t, the indicator of I naught t minus x. We get this phase vector right here, and we get Ij naught hat at s minus t. Okay, so that is nice enough. But then, well, we want somehow f to be localized in this representation at one single spot, one single interval. If we assume, for instance, that J naught and I naught have the same kind of scale, this Fourier transform should be supported on an interval around S, and this should be supported on an interval around X. Right? Because we're translating this by X and this by S. So if J naught has kind of a similar scale to I naught, the supports are gonna be kind of very different if S is very different from X. So we make an innocent assumption, which is that, well, X equals S, just so that we actually localize on a single interval, and let psi be an arbitrary real number. So we get that our Fij, or attempt at a representation for our functions, at a time frequency localization for our functions, actually has the following form. So it is something like an integral on R of f of t, e to the minus 2 pi I psi t, times phi of t minus s bar dt, where phi is just like this, this localization function, this, what we're going to be calling in a short while a window. Okay, and this motivates the definition of a short time for a transform. So actually, the short time for a transform is exactly this. There's nothing else. It's just that it's just a way to, well, if you think of the most, I don't want to say naive, but the most straightforward way to define a space frequency localization of a function, which is the one we use, then you get naturally the definition of a short time for a transform. So this is going to be the object that it's going to be the main focus of our lectures, and let's just go through that with a little bit more detail. So the short time for a transform, it has a window function g in L2, which is going to be this translating parameter here. It has a modulating factor, and it is as a function of the variables x and psi, right? So actually, I need to, in order to compute the short time for a transform x at a point in R2, I need to tell you how much I'm translating my window. So this window is telling you nothing but where you're localizing your function in space. And this is a modulating factor, which is taking you for a transform of that. Okay, so we need both of these parameters. So this is like the frequency translation parameter, this psi, and this is the space translation parameter. And just in order to drive this point home, so if we take G to be identically 1, we recover the usual Fourier transform, right? So this just becomes the Fourier transform, and X doesn't play a role at all. So G equals to 1 might be a bad time frequency representation because it doesn't give you any extra information depending on whether you're changing the window or not. But then if we take G to be a different function, right? That is not necessarily identically 1, so that it has some sort of space localization properties. Then when we change X, we're just like adjusting the frame to which we're actually taking our time frequency picture of our signal. And then once we adjust that frame, we take Fourier transforms. And this is more or less what's illustrated in this picture. And here, like each vertical line represents a Fourier transform, or the magnitude and absolute value of the Fourier transform of the function f of t times g of t minus x. We're translating the frame according to the point x that we want to analyze, right? And it's going to give us, as we see here in this picture, kind of a time frequency picture of how the frequency align, how the frequency is distributed over time. So, and this is kind of what we were seeking, right? We were seeking something that tells us some information that if we only look at f or f hat, we won't have this picture. This picture is not there. But as soon as we take some sort of localization in space and a localization in frequency, we get some sort of joint distribution, which is actually, well, don't quote me on that. It's just the words of Grötting. It's actually what the ear does. It's kind of seeing both space and frequency at the same time. It's hearing space and frequency all together. Okay, so let's maybe stop and take a look at a couple of properties of the short time Fourier transform. don't worry about these things too much. I'm gonna prove almost all of them in a short bit. So let's maybe go through them. The first one actually just says that if I have G and F, so a window and a function F, actually, I can compute the short time Fourier transform with the window G hat at the function F hat by just looking at this original short time Fourier transform. We just need to invert the parameters, or this is supposed to be C and psi, not an omega, or this is supposed to be an omega in case. So there's this pretty useful formula, which kind of shows that this short time Fourier transform possesses a certain sort of a Fourier duality. Well, the second property just says that the short time Fourier transform in absolute value has frequency and space translation symmetries, right? So if we take a frequency translation is just a modulation, right? If you take a modulation of F, this is translated as a translation of the short time Fourier transform in the second variable. And if you take a translation of F, this is translated as a translation in the first variable. So we're kind of like this time frequency representation. It's very well adapted to translations both in space and in frequency. That's what the second part is saying. The third part is saying that actually we have a Plancher out there for the short time Fourier transform. So if we want to compute BG1 F1 inner product with BG2 F2, then this actually decouples to just B1 B2 in L2 times F1 F2 in L2. And in particular, this is going to be very useful for us in the remaining lectures. If you take the windows to be the same, then BG is an isometry from L2 of R to L2 of R2. So this representation, besides having some nice symmetries, it is also isometric. So it actually also captures kind of like the metric structure of L2, right? So it's more evidence that this representation is actually useful, right? And finally, you can actually recover F by just averaging out this this VG of F. Well, with respect to the group of symmetries. In which way? Well, we just multiply VG of F at X psi by, well, take H, just an arbitrary function in L2, translated by X, modulated by psi. This is supposed to be evaluated at this is supposed to be Y. This is supposed to be evaluated at Y. You integrate, you take averages, you divide by the inner product of G and H, and you should be able to recover F. So let's maybe break down a couple of those properties. So let's go maybe for the first one. Okay. So how would we prove the first one? So let's just write this thing in the following way. So the short time Fourier transform at X psi can be written as an L2 inner product of M psi Tx of T. So this is an inner product and L2 real line. But then we use Plancher L. So by using Plancher L, this is just F hat T minus psi and X T hat. And this is e to the 2 pi I X psi times F at mx T minus psi of G hat. And then we come back, right? So we just from here, the only thing non-trivial that I use here is that we can use Plancher L, and the Fourier transform takes modulations to translations and translations to modulations. So this is equal to, so this is exactly what we want. So this is 2 pi I x psi dg hat f hat at psi minus x. Right, so this proves the first one. The second one can be proved by just directly inserting into the integral, so we're not bother doing that. Let's maybe prove the second one as well, the third one, sorry. So the third property, so this in a product property of the short time for transform. It uses a different expression for this guy. So the short time for a transform at x and psi can be written like this, but it can also be written in the following form. So Vg of f of x and psi is just f times the translation by x of g bar or a transform at psi, right? So that's a pretty straightforward way to write it. So we just write this, let's just write out what this L2, what this inner product in L2 over 2 is. So first we have an integral inside of F1 times Tx G1 bar, where transform at psi times F2 Tx of G2 bar, where transform at psi, all that to the bar, v psi dx, right? Right, but now we have an inner product in the psi variable to Fourier transform. We use Fletcher again. So this is just integral in R. By using Fletcher, we get integral in R of F1 dx v1 bar, F2 dx g2 bar, dy dx, and then we just see that this is actually, let's just replace it by g1 of y minus x bar. This is just g2 of y minus x bar. We change the order of integration. We integrate just this guy, which becomes independent of y. And we should get exactly that. Oh yeah, sorry. There's a bar here. There's a bar here. So there should be an F1, F2, L2, and the V1, V2. I think you might have made a mistake. It should be with the bar. But the bottom line is that you can kind of decouple the inner products for those guys. And finally, there's the last one, which is this recovery formula for F from its short time for transform. Maybe we go for a term just very quickly. This is recovery for. What is the integral in R2 of Vg f of x psi m psi t x h y dx? Right. So we just use again the definition of the short time version. Okay. Okay, so maybe we can write it as an integral of f of t on R upon changing the order, right? Upon changing the order of integrals. Let's suppose that everything is nice enough that we can use Fubini's theorem and all that. But after changing the order of integrals, we'll get something like this. So we have an integral in R2 of e to the minus 2 pi I y psi times h of y minus x, which is this term right here. And then what we have from BGF, which is the same thing, but with the window g. So I have g of t minus x bar e to the 2 pi I Right, so maybe, I think it's like this, maybe like the n minus psi. But yeah, we have something like e to the minus 2 pi I t plus psi. And then we integrate the variables x and psi, and here on t. Okay. So the variable x, we forget it at first, and we integrate it psi. So in the sense of distributions, this is just going to be like the Fourier transform. This is going to be like integral in R of t, integral in R of h, y minus x, g t minus x bar, times the integral of e to the 2 pi I y minus t psi psi. Here we have dx, and here dt. Okay, but this is just a delta, right? So this is the delta of y equals t. So this thing here will all come down to this whole thing vanishes unless y equals t. So we have the delta carries over to f. We're going to have f of y times the integral on R of h of t minus x because of the delta x, g of t minus x bar dx. But this is just exactly what we're claiming that it was. This is f of y times h and above it is g. Right, so we can recover our function f. But just taking averages of the short time Fourier transform over each group of symmetries. Yeah, it recovers the function half point wise. Okay. I think it's this was a good warm up to kind of like see how the different definitions of the short time Fourier transform actually come into play. So,
Excuse me.
sure.
If I see correctly, the left hand side depends on y.
Yeah.
Right hand side, I do not see y. There is, sorry, there is. Okay, I see.
Yeah, yes.
I'm sorry.
Yeah.
Okay.
No, absolutely. Yeah. It just comes into play in a very subtle manner here in this delta thing. Yeah.
I'm sorry.
No, absolutely. Yeah, thanks for the question. I was about to ask whether it was clear because it's a bunch of computations, right? So sometimes it's easy to mess something up. I'm sorry in case I did. Well, so let's maybe this is all well and good, but let's maybe go and try to prove something more interesting about this about the short time Fourier transform, right? And oh, actually, no, I forgot to include these slides. Oh yeah, I was talking about the wavelet transform. Yeah, sorry about that. So it's just a quick digression about the wavelet transform. So yeah, so actually this part 2, not part 3, sorry about that, highlights that the short time Fourier transform has these translation invariances as I mentioned before. So it kind of looks very nice if you translate the function f or translate that path. It's translated into a translation of the short time Fourier transform of f, regardless of what window you pick. But then you might think, well, if I don't want my operator, my end operator, my time frequency representation to have these kinds of symmetries, so these double translation symmetries, but if I wanted, for instance, to have a symmetry with respect to horizontal translations to space translations and to dilations, what do I get? What kind of operator should I get? And as a mathematical question, this is completely valid, right? So what kind of object can we define? And the mathematical objects that is associated to this group of symmetries is the wavelet transform, again with the window G, at a function f, And it again has two parameters, x and s, but now x is a real value parameter, and s is just a positive, a non-negative real value. Rather positive than that, but and it's given by just this expression, which is again very similar to what we had with the short time Fourier transform. It's like an L2 inner product of f, but with a translation of a dilation of g instead of being a modulation of a translation of g. So it's kind of encompassing the dilation symmetry that we wanted. And just before we move to a couple of more interesting facts about the short time Fourier transform. Let's maybe mention that the wavelet transform, which is going to appear every now and again in our discussions, has also some very nice properties. So the first of them is that it has also some inner product, nice inner product decoupling thing, right? But right now, instead of considering the Lebesgue measure on the whole space, I need to consider the upper half plane with the Lebesgue measure on the horizontal variable and with ds over s squared in the vertical variable. So it's kind of hyperbolic metric on the upper half space. And with respect to the inner product, we get the decoupling identity as well. So we have that the inner product with WG1F1 with WG2F2 is just the inner product of F1 and F2. And well, let's assume this is just the Hardy space of the upper half space, so the inner product induced by the Hardy space. And this is the inner product induced of G1 hat of G2 hat by L2 with respect to the dt over t matter. Okay, this is just to highlight, don't pay too much attention to that. It's way uglier than what we had for the short time Fourier transform. It just says that, well, actually, the wavelet transform has a very nice property of, if you want to compute inner products of WG1 and F1 with WG2, F2, it's possible. You have a very nice relationship. If there's norms, if G1 equals G2 and the norm is 1, then this is an isometry, and we're going to be talking more about these cases later on. Right, also, yeah, the wavelet transform has exactly the symmetries I described before. So if I take a translation of F, this is just this is translated into a translation in the x variable. Sorry, they're switched here. They're swapped. It should be like the b minus x in the first one. It's if I take a translation of F, this is equal to a space translation of the wavelet transform. And if I take a dilation of F, this is just a dilation, but without normalization of the wavelet transform. Okay, so it has the properties that we wanted. It behaves well with respect to space translations, into dilations. And if you average right now, not over the group of modulations and translations, but if you average over the group of translations and dilations, you should be able to invert this operator in a similar way as you do with the short time Fourier. But this is just a brief introduction, since this operator is going to be appearing every now and again in our discussions, just so that you familiarize yourself a little bit better. Don't worry too much. These properties are going to come back whenever we're going to be talking about the wavelet transform more in depth. Okay. So maybe the philosophy, we highlight exactly this philosophy that whenever something holds for the short time Fourier transform, a kind of a hyperbolic version of that should hold for the wavelet transform, and then for that reason we focus on the short time Fourier transform for now. Okay, so let's go maybe for what I wanted to show you guys today very quickly. So the reason why we defined the short time Fourier transform was in order to localize sharply a function in space and fields, right? And then the question is, how well does it do this job? So does it do? Can we actually localize? So the question is, let's fix a window G, and let's take a function f. Is the short time Fourier transform efficient at localizing its support on a reasonable set U, and at which scale? As you might just see from the way we define stuff, it's a very flexible question, right? We can determine the function G, we can change the window, we can change the set, we can change actually the notion in which we want to fit the short time for a transform onto the set Q. And, but we have to start somewhere, right? And the way we started is just like by noticing that you cannot focus, you cannot concentrate too much on a set U unless the set U has non-trivial measure. This is a very weak conservative principle for the short time Fourier transform, and its proof is just a line. The short time Fourier transform, the way we defined it, is just bounded pointwise by the products of the L2 norms of F and G. They were 1. So this is pointwise bounded by the measure of U, but we had the lower bound 1 minus X. So this is a pretty good result. We're not doing anything. We're not exploiting cancellation, not doing anything. And the question is how sharp that is. And it's not so sharp. It should be sharp because, well, you're concentrating almost all of your mass over a set of finite measures. This set heuristically should be gigantic, should be very, very large. As it turns out, this is still an open problem. So this is just like talking about that on Lassonde, but this is like for general Windows G, showing that whenever I concentrate too much on a set U, then the measure of U is uniformly bounded from below by something that goes to infinity, only depending maybe on the window work, but I don't know. This is an open problem. The only window for which this is currently known is the Gaussian window, but I'm going to be talking about that in a bit. And I am working towards a proof for other Hermite functions as windows. But for general functions, this is not known. So the measure of U has to go to infinity, as this epsilon goes to 0. But just already saying that there's a lot of room for improvement in this area. It's also a very new thing. So the new results and the very nice recent results in this area are from, I don't know, the last 3 years or something like that. So that there's still lots of room for improvements. But then let's maybe try to take a look at a more modest goal, which is that of trying to prove that a slightly better bound than this lower bound, that the measure of U is 1 minus epsilon. And this is what Lieb's uncertain principle for the short time Fourier transform does. Okay, so what did it say? Well, let's consider the same setup as before. F has L2 norm 1, same as G. And take a set U, subset of R2, such that for some epsilon greater than 0, this integral on the set U of the short time Fourier transform squared is at least 1 minus epsilon. Then under those conditions, the measure of U is bounded from below by this quantity for all P. And hence, as a consequence, if we optimize it on P greater than 2, we get that the measure of U is bounded by 2 times 1 minus epsilon squared. So it still doesn't achieve the goal that we wanted, right? To show that the measure of U is bounded from below by something that goes to infinity, but it's still, well, 2 is better than 1, which is what we had in the previous case. So it improves a bit the previous result. And as we shall see, it's already very non-trivial to get this thing. You need to use several inequalities, several sharp inequalities in harmonic analysis in order to do that. So let's maybe start with the proof. So the proof goes through this very beautiful inequality also to Lieb, which is an estimate on the LP norm of the short time Fourier transform for P between 2 and infinity. So it just says that, well, if I take F and G now 2, then the LP norm of this guy raised to the P is bounded by 2 over P times the products of the LP norms of F and G to the P. Okay. So it's a very, and this is actually sharp. It's sharp, and the only equality case is when F and G are Gaussians. So Yeah, this is a very beautiful result, and as we shall see, it's a product of the Sharp-Hausdorff-Young inequality and the Sharp-Young's convolution inequality. So let's maybe see how to prove this, how to prove the asserted principle in Leibniz inequality. So let's assume Leibniz inequality first. So by assuming that, we prove Leibniz asserted principle, and how is that achieved? Well, take suppose that we're normalizing, as in the statement of the asserted principle, the L2 norm of F and the L2 norm of G to be 1, and suppose that our integral of Bg of F squared concentrates the order 1 minus epsilon on the second unit. By Hilbert's inequality, we have this very simple, we use Hilbert with P over 2 in its conjugate, right? This very simple estimate, just following from this. But then we use a Leibniz inequality with this first factor. So we just do something very lossy, to be honest, which is just saying, well, replace U by the whole two-dimensional Euclidean space, and use the previous inequality that we had. This will give us this explicit bound for the first factor. Sorry, this should be a square times this second factor right here. So when we multiply, since the L2 norms of F and G were 1, we're going to get this is an upper bound for 1 is epsilon. We just rearrange terms and we get exactly what we had there. Okay. And it follows directly from that. So the last thing that we need to do here is to prove Leibniz uncertainty, Leibniz inequality for the short time for transfer. Okay, and that is as I said, it uses a couple of things as black boxes. So the first one is this beautiful theorem by Beckner, and later on the equality case here was characterized by, I think, Braskin and Lee, which is a Sharp-Hausdorff-Young inequality. It says that, well, whenever p is between 2 and infinity, then the LP norm of F hat is bounded by p prime to the 1 over p prime over p to the 1 over p, all that square root, times the LP prime norm of F, writing F and LP prime, right? So this is the first statement that we're going to be using this one, and we're going to use also a representation that we're already familiar with for the short time Fourier transform. The short time Fourier transform at x and omega is just f times the translation of g hat for a transform at omega. Then let's go to work. Okay. Then let's use Beckner's result on this thing, right? So these are just like the integrals on the vertical variable, on the omega variable of this LP thing. So this we rewrite as a Fourier transform, which by Beckner's result is bounded by this. Nice, cool. But then here we notice that this is f of y times g of y minus x, all that raised to the p prime power. In other words, this is just a convolution of f to the p prime with g to the p prime at the point x, and you raise that convolution to the power of p minus 1, and you multiply it by the constant that you get in front. Right. So the vertical variable is dealt with, and we bounded it by something like we're able to majorize it by something like a convolution in terms of x. Okay, let's then look at what we can do with this. So if you integrate in the other variable now, we're just going to see that at the end of the day, the LP norm of the short time Fourier transform is bounded by this factor times the p minus 1 norm of this weird convolution. And then what do we do with that? Well, fortunately, Young's convolution inequality also has a sharp version. And its sharp version is the following. So just quickly recalling for those that might have might not have this impression in their minds whether the constants, what the sharp constants are. If we define A as to be just this ratio, this square root ratio, For any triple of indices, PQR, that are admissible for Young's convolution inequality, the inequality holds. The usual Young's convolution inequality doesn't include this factor up front, but we can actually improve it to putting this product of these three constants. So each of these constants is less than 1, so we get an improvement over the usual Young's convolution inequality. Okay, so we do that with the right indices, right? So those right indices are going to be, well, R is going to be this guy, and P and Q are going to be these two other guys. So finally, if you do all the computations, everything goes very well. So you get like this bound times the L2 norm of F to the P prime times the L2 norm of G to the P prime. And finally, putting it all together, we get that the LP norm of VG of F raised to the P is less than this product right here times the L2 norm of F, L2 norm of V to the P. And the magic, which I am not at all going to show you guys, is that this whole hideous product just reduces to B2 over P to the Pth power. So whenever you do the computations for all the constants, it just reduces to a very beautiful 2 over P to the Pth power. And this finishes the proof. So then what is the main message behind this proof? Is that, well, sometimes for the short time for a transform, you can analyze it sometimes by like fiber by fiber and still get very sharp inequality. That was actually what happens exactly here. When you analyze fiber by fiber, you see that the equality holds, as mentioned here, for Gaussians. In fact, there's an equality that is characterized by Braxton and Lee. And the equality in the sharp Young's convolution inequality was also characterized by Braxton and Lee, and it's also for Gaussians. So the equality cases match. And actually, if you plug in Gaussians, you can compute, we're going to see that in the next lectures, you can compute very well what VG of F is. It's just like it's just a Gaussian on C, on R2. And you can see that everything, each and every one of the estimates that we did is completely sharp, and that the equality is attained if if we have Gaussians as windows and as functions that we include. And yeah, so that is the result that I wanted to show you guys for today. Just a couple of remarks before I finish for today. An analogous result is available for the wavelet transform, but it's not as easy. Why? Well, we don't have the short time for a transform has this very nice representation. For the wavelet transform, we need to use Poincaré and represent it as a Fourier transform of F times the dilation. And then instead of working on R, we need to work on R with sums and differences that is like under the additive group with R as an additive group, we need to work with R plus as a multiplicative group. We need different versions of the Hausdorff-Young inequality. The Hausdorff-Young inequality just the same, but we need different sharp versions of the Young's convolution inequality for locally compact abelian groups, and I didn't want to show that today, because otherwise you guys would be even more bored than you probably already are. But yeah, this is just a note.
Are the extremals known for the wavelet transform? Is it the Gaussians?
That is a good question. I'm not sure. I was looking into this paper of Kahneman's Koschenik, and he basically doesn't really answer this question. He says something about would be nice to look at extremals. Maybe it's like this.
Yeah, because it doesn't seem obvious to me because of the these results on the Lie groups.
Right.
Are a little bit more complicated.
I think I would. Yeah.
They're not known in general somehow, I think.
Yeah, I would also be very surprised if they are known for the wavelet transform. I don't think that. To be fair, the only result I found on this was this by Koschenik, where he doesn't even do that at a very concrete level. He just says, "Oh yeah, let's do it for locally compact abelian groups," and doesn't specify to the wavelet case. So it would be, yeah, most probably it's not known what the extremals are for the wavelet transform. And just a couple of yeah, but thank you so much for the question. just a couple of different remarks. So this inequality, as I said, is sharp. Equality holds if and only if f is a Gaussian. And the more interesting remarks, as I said before, is that it improves the weakness of the principle, but it is far from sharp, as we would expect that the measure of sets, of these concentrating sets, should go to infinity for any given fixed window, but we don't have a proof of that. And in particular, in order to try to prove this result, it induces the study of these kinds of quotients, right? So we try to, for a fixed set U, you want to take a look at a function that best fits into that set, right? So that such that its short time Fourier transform fits the best possible way in space and frequency into this set U. And this induces this is a good motivation for the tomorrow's lecture. We're going to be looking a little bit more into this in depth into this concept of time frequency localization operators, which for which this quotient right here is going to be exactly the square of its first eigenvalue. So we're going to be able to relate in the next lecture the short time for a transform with some compact operator in a Hilbert space and its spectrum and the analysis of its spectrum in order to try to answer these questions of concentration. But yeah, so I think that's all for today.
Thank you very much. Are there any questions? No. Could you place in time the results from the previous slides? I mean, the inequalities by Beckner, Leap, and so on.
Yeah, so this I think it's from 75.
Yeah.
Yeah, this is from so this inequality is also in the same paper from 75, and I think this is from 80 something. I'm not entirely sure. This paper by Lieb and Braskamp Lieb later, or maybe it's
But there was an early results of Beckner, the Hausdorff-Young for even integers.
oh yeah, that's by Babenko as well.
Yeah.
Yeah, that is from the 70s as well.
That's from the before Beckner.
Exactly. Yeah, that's a little bit before Beckner. Babenko showed the exact same thing, but for even exponents.
Right.
And also for the constant. For the constants.
What?
The constants.
Of course, that was the only issue.
The five of the constants.
Yeah,
Yeah.
exactly.
Yeah, that's a surprise because it's
Exactly. Yeah, and yeah. So this is from these results are from the 70s and 80s, and yeah, this one that I was showing right now by Lieb is from late 80s, beginning of 90s, I think. So these things were produced back then. Like this is a short note by Lieb, and he was interested in some physics problem. And
But was he thinking along these lines, Lee, or was he proving in his mind a different type of inequality?
that's a very good question. I took a brief look at the paper, and I think he wanted to prove something else for like a physics model, and he ended up at this inequality. But I think he didn't notice that he had applications to the concentration inequality. I think the one who noticed that was Gresham.
Okay, that makes sense.
Yeah. Yeah, this result by Gresham is from later on. So from like the 90s, I think.
Any other questions or comments? No, then thank you very much, João, for the talk, and we meet back tomorrow at 10. Now is the time for